All right, welcome back. We are Game 2005 in the fall 2020 semester at George Brown, and it's Game Physics. And it's week 10, actually, part 1. And where we are is we're sitting here. Today we're talking about 2D collisions and optimizations. And one of the optimizations that we just talked about actually was a some kind of object pool, all right, which is something we can use, right, to make our game better, and I'll talk about that a little bit. So we're going to talk about that today. Next week is collision response, and then 2 weeks from now, and I'm working still on getting you a 3D structure for you to use, you'll be getting assignment 4, which is going to be using 3D collision detection and response, right? So that's kind of something that we're going to be working on, and I'm working on that with Alex to make sure we have something for you by week 12. Okay, so that's coming up. So let's start with the stuff that we're doing right now. So guys, most of you know how to do collision detection, and we're going to talk about this in brief. And this is 2D collision detection that we're going to be talking about today. I'm just making sure that everyone knows, and this is more of a formal discussion about 2D collision detection, not the stuff that we talked about in fundamentals or that you did last semester or anything like that, but more of a formal discussion about how things work from a physics perspective. So really, at the end of the day, you want to make it so that your collisions are believable and somewhat realistic. And the idea in your mind should be, is it good enough? Is it good enough? Why? Because we can get really super pixel perfect collision detection. And the problem with that is once we get pixel perfect collision detection, it becomes cumbersome. Okay, and I mean that in that the calculations that you have to do every frame go up a lot, okay? And so we have to start thinking about the, kind of solutions to our problem, which is I want to use something that is going to satisfy requirements. It's going to look good. It's going to be, there's going to be both a logical collision and a visual collision that match, right? And that produce the effect that we're looking for, okay? So again, when we think about it from a physics perspective, detecting collision of two objects is really objects that can't occupy the same space. So they're trying to overlap somehow. In real life, obviously what's happening is collision happens because the molecules of one object connect or collide with the molecules of another object, and we have to go through that Newton's laws thing, which basically says for every action, there is an equal and opposite reaction. Who remembers which one of Newton's laws that is? If you do, put up your hand, and then maybe put it in your chat. Which Newton law says that for every action, there's an equal and opposite reaction? Third law. Thank you very much. And that's exactly what we're talking about here. So that's response. So one part is the collision detection itself. Did I collide? And the other part is how did it work when it came to yes, Kira, I wish that things happen at a molecular level. But really, that's what happens in real life. That's what we're saying. So how did I collide? And then what happens is we're also going to be talking about momentum. We talked about that last week, where momentum plays a role, right? Because we have energy that's being transferred across a system boundary. So there's a lot of times what we do, there's games that do some kind of spatial hashing. They use some kind of static grid, and a lot of times, especially when we have many objects that are colliding, we use something called broad phase collision detection. Broad phase collision detection means that we split our screen into quadrants, and we keep splitting it recursively so that we can see that is there something to collide with. Sometimes we also use a voxel type collision, where we split up our world into little bits, if you will, tiles, like 3-dimensional tiles or 2-dimensional tiles, where I know for a fact that if there's no one that's inside of my tile, then there's no possibility that I can collide. What do I mean by that? Well, sorry, I was talking about optimizations earlier. We're going to come back to this picture in a sec. I'll just redraw it. All right, so think about this. I have a grid, let's say, right? And if I have my screen here, and I split up my screen into halves or some kind of quadrant. Okay, so let's say I have this part of the screen. It doesn't matter if they're equal. I have this part of the screen. I have this part of the screen. I have two objects. Let's say, for example, I have the player object down here, and I have the enemy object up here. Should I start doing collision detection now? That's the question that spatial hashing does, or the ability for us to, kind of cut our addressable space into pieces? The answer should be no. We shouldn't start doing collision detection. So broad phase basically tells us, okay, let's split this screen in half again. And how about I want to find out where I am, so I'm going to split up my screen here in half again. Let's say approximately, and in half again. And I'm going to keep doing that until, right, I kind of figure out which part of the screen I'm in. I could be in more than one piece. And what I want to do is I want to say, well, okay, if this is where I'm at, this is the location that I'm at, do I see anybody within these four tiles? And the answer is no. Well, then don't do collision detection. Right? So that's kind of how it's done. It's usually in some kind of hash or a separation, if you will. And this spatial partitioning, this idea of spatial partitioning, is broad phase collision detection. Now, there's a cost to doing this, right? And if you have a lot of objects, let's say, for example, I have many objects way out here, right? So let's say lots of objects up here, right? And I don't need to do collision detection with all these objects until an object becomes kind of in here. Now you see that here I have an object that's near me. If the object is in this place, is it close enough to touch? Well, let's split it up again. So we just kind of go through here and we go, okay, well, let's split this little place up here again. Am I in the same tile? Well, this part is, let's split this part again. Am I in the same tile? Right? And you can split it so you see that maybe it's not in the same tile. Sorry, my drawing is a little off, but even if it is, let's split this up again, and you can see that, are we in the same place? Do I have a collision detection? You just keep splitting it and splitting it over and over again. This recursiveness takes cycles, although it can be done very nicely in from a 3D perspective, right? If I have my object here colliding with this object over here, right? So what happens is, I don't do collision detection out here, and I start doing it in here. What happens? Inconsistent gameplay, my friends, right? Where we have, especially when I have thousands of objects, you might see your game slow down a bit. Where we have a bunch of objects, nothing's near the player, but as soon as objects start coming near the player, we start doing collision detection. And that gives us inconsistent gameplay. So we have to watch how we do our broad phase collision detection. So that's this idea of a spatial hash or a spatial partition. Where we kind of split our screen or our addressable space into, quadrants, if you will. Narrow phase is when we get close enough. So the narrow phase happens when we're close enough to the collision detection so we can start actually using our overlapping algorithms. Things like, as an example, AABB style collision detection, which is really just an overlapping technique that we're using. Okay, and we'll talk about this in a second. So really, the simplest, the most basic type of collision detection is a sphere or a circle, right? And really what we want is, there's 2 points to think about, the center and the radius when it comes to detecting collisions, right? Here's an example. If I have, I'm going to create a boundary, right? So here's a boundary that goes around this three-dimensional object. Even though we're not talking about three-dimensional objects today, it's the same as if I want to put a boundary around an object. Now, you can see that this is not the most efficient use of my boundary. Why is that? Because I have a lot of empty space over here, and I have a lot of empty space over here. And so what I can get sometimes is this logical collision. So programmatically it collides, but a visual collision, that fails for us. We look at it and go like, wait, that shouldn't have worked. Why do we get that? That's wrong, kind of thing. And so we want to understand we think about the system boundary. Really, when we think about our system boundary, when it comes to collisions, it's our collision bounds, if you will, or our collider boundary. When I think about my collider, is almost like it's the same thing as my system boundary. That is the edge or the skin that I'm going to be using on my game object to overlap with some other game object. If an overlap exists, somehow I have a collision. If an overlap doesn't exist, then there's no collision. All right? So here's the simplest of detection algorithms, where I have these two circles. As an example, I have a radius R2 and a radius R1, and then I have a distance between centers, so between this center and this center. If the distance between my centers is less than the combined radii then I have a collision. Why? That means that this radius is inside of this circle. It kind of goes into this one. And we can simply draw that again if I go back to my little drawing board up here. And let's see if I can accomplish this without making too much of a mess, right? So again, I have a circle. Here's my circle. And if I draw another circle inside of it, right, as an example, there's an overlap, clearly. But what I'm saying is, if you take the radius of this circle, see how the radius of this circle kind of goes into the other one? Well, if you have that situation where the radii overlap, just go into the other circle at all, you have a collision, right? But the other way to detect it is the distance between centers. If the distance between centers is less than these, that's cool. But now we're talking distance detection. Distance detection requires typically square root. I want to calculate the distance between two vectors, right? And whenever I calculate distance between two vectors, square root's being involved. Square root every frame is a bad calculation, my friends. So we don't want that. Instead, what we want to use is squared distance. And by the way, I'm going to pull up our little engine that I've given you guys, right? That me and Alex kind of developed. So I'm just going to go into that just one sec. I'll bring it up. So here's our little engine, right? And let's bring this up. Now I'm running, as of this video, I'm running to make the engine 3D. That's what I'm doing. So I'm using OpenGL and an SDL context, but it doesn't matter. Don't worry about this for now. What I want to show you is when it comes to collision detection and everything else that we've given you. So if you notice that there is a collision manager that comes with the engine, right? So here's a collision manager, and these are all the collision detection checks that I've given you already from the get-go. You've got something called a squared distance, right? Squared distance between two vectors, a vector 2 and another vector 2, 2 points, right? And if I actually looked at the details for this one, so if I go to definition, right, then you can see clearly what's happening. I take a look at the vector, I get the difference of x's and the difference of y's, multiply them together and add the results, and that is the squared distance. Squared distance, wait, I need the distance. How do I compare the squared distance? Well, I can do a squared radius check where I take the half the heights, or the radii, and I add them together, right, as an example. And once I add those radii together, I want to square those, so I square those, and then I compare it with the squared distance. So if my squared radii is kind of the distance is less than the squared radii, I'm comparing squares here, it's the same as if I'm doing square root, right? And so this way I can avoid doing a square root detection check, right? The distance. And if I can do that, I'm saving myself cycles. Remember, especially if I'm doing distance checks with many, many objects, that is there's a higher computational cost from a big O notation perspective than, as an example, for doing something like a simple AABB overlap. Okay? So that is circle detection check, where you have two radii and you want to, just to see if the distance between centers is less than the radii combined. And here is the pseudocode for this. By the way, we have this inside of our code. So if you go back to your engine, if you want to actually look at the distance. So I have an AABB check. We're going to talk about that in a second. But we also have a circle check, right? And the circle check, where do I have it? So sorry. We also can compare circle AABB. But basically what we want to do is an actual distance check between the two centers, right? I actually don't have that in here at all. But, and why? Because it's computationally expensive to do a detection between, to do actual radius, a true radius detection, right? All right, so that is the way we would do it with some kind of collision manager. Now, I want you to notice something about this collision manager, right? This collision manager does not use a singleton pattern. It is a static function. and that means it's not thread safe. So if you're going to put this in multiple threads, this collision manager would fail. And we've made it like this on purpose so that we can modify it later on and create a singleton pattern. All right, if I wanted to make a collision manager work like a singleton. And you should know what a singleton is by now. But let's go back to our code. I mean our example here. So this is the way it's done. So we get the radius, we have a circle. The circle itself can be defined as a radius and a center, x and y. And what we want to do is we want to get the distance between these and use the math.square root function. Again, a very computationally expensive function. And by the way, division or even the power, we definitely don't want to do both. Some people actually program both in their distance check. So if I was going to look at the distance check, going back to our code, I have a utility function that I built for you guys as well. So if you look at the utility function, there is a squared distance check in the utility function as well as a distance check, right? Different distance checks. So if I go to the distance check, then you can see that's exactly what we're doing. There's a distance check. I'm kind of comparing the distance between two vectors. Okay. Now I could do x times x and y times y, and I'm using the square root function, or this would be crazy, I could use power of 2. Guys, if I use power or square root, and if I use power twice, that means it's like 3 times less efficient, because power is really, square root and power are the same things. We don't want to use power and we don't want to use square root. So that's why we do x times x and y times y. If we use power in here, it'd be even worse. So please don't. All right. So again, it's pretty straightforward when it comes to detecting the distance between two circles, because that's the easiest detection, and a lot of times it can solve a lot of our problems. Why is that? Because again, we want to see what's good enough, right? So again, if I have a very circular type object, right, and let's see if I can find one. I'm just going to look for a random circular ship online. Let's take a look at that. So I want to say something like ship sprite, random, right? Hey, there's a ship sprite, and we can certainly use this ship sprite. I'm just going to download it now. So I'm just choosing a random ship sprite online, right? So let's just put it on in my downloads for a second, or actually I'll put it in on my desktop inside of our GBC there, right? So there he is. So ship 11, sure, we'll call it ship 11, doesn't matter. So when I go back here and if I want to load it, so let's I want to grab ship 11 and kind of paste it in, right? So let's go there. So here's ship 11. Very circular, right? And I want to grab this thing and I want to copy it, and hopefully I can paste it inside of my area here, which is pretty cool. What I want to do is I want to talk about this this silly shape. Now it's clear that I could use different collision detection methodologies here, right? I could use a box type collider, right, where I can draw kind of a boundary box around this object. That is the simplest way of doing collision detection, right, where I can draw a boundary box. But the problem is that I have an area here and I have an area here, here, and here, which is not going to provide a good visual collision. It's going to provide a good logical collision, and the simplest one is a box collider, I would say, right? Maybe just as simple, if not simpler, from a coding perspective than using circle detection. All right. So that is the problem with this situation. But what if instead I used a circle? Right now you can see that my boundary area is much closer. Right, I have less in here that is going to provide a visual distraction and take me out of kind of my it's going to take me out of the immersion of, hey, it's actually colliding. Now it's not perfect, okay, but the question I ask you again is it good enough? Is it good enough? If it's not good enough, right, then we need to do we have to solve the problem with using other means. Okay, so in this case we have a single collider shape is what we have, and the collider shape, we want to try and match it with the game object as much as possible. Another basic geometric shape is the cylinder. right? And if you think about a cylinder, what it is, it's just a rectangle, right? And the rectangle has two circles. The cylinder has two circles at each end, right? So a circle at the top, a circle at the bottom, right? As an example. With a cylinder, I mean, really what we're doing is we're sweeping the circle in 3 dimensions. That's what we're doing. We're kind of, moving the circle so that it goes in 3 dimensions. And let's use Blender to visualize this when we think about this for a second. Hopefully my Blender today will open up and it's not going to cause me any consternation. All right, so again, I want to go to put together, you can use whatever you want in Blender. For example, if I want a circle, I can use a circle in Blender. And suppose I want to extrude from a circle shape. Okay, so I want to go into, as an example, edit mode in Blender. Don't worry about the hows right now. But if I select all my verts in Blender, right, and I press E for extrude, and then I extrude upwards in the Z direction, you can see that all I'm doing is I'm extending the vertices in one direction. So I'm sweeping the sphere from the bottom to the top. So really what it is in a cylinder, I'm just taking a bunch of circles and I'm just extending them across the entire distance, right? So what do I have? I have 2 circles, circle at the top, circle at the bottom, and then a distance between the circles. And then it gives me 2 things. The radius still applies. I can still use the radius. Plus, I can use the distance between centers. The distance between centers, or the height of my cylinder, is something that I can use to calculate collision detection. Okay? So pretty straightforward stuff. And it really talks about that if the distance in the XY plane from the long axis of the cylinder to the surface of another object is less than or equal to the radius, this is really the formula right here, then a collision has occurred. Okay? And it talks about here, how do I make methods of making a collision sphere around an object. What I want to do is I want to, kind of put it so that the object is inside of it. And collision spheres and collision shapes are the basic ways we create a bounding box, a bounding area. Okay? Now we're going to talk about bounding boxes because bounding boxes, and there's 2 types that we're primarily using. You've already know about the axis-aligned bounding box. Alex would have talked to you about this probably in fundamentals, or I did. One of the 2 of us probably, or someone else. Maybe Joss did, or someone else did. Or maybe you learned it on your own. And it's also called AABB type collision detection. Again, we're just trying to fill in the holes here, guys. If you already know about this, bear with me. Because everything, the basic collision detection can come from this, right? If you think about it. There's also something called object-aligned bounding box, and this we can derive separating axis theorem from our object-aligned bounding box, right? Which is different than our axis-aligned bounding box. So again, when we define an axis-aligned bounding box, we're saying that the 2 boxes using the same axes, x and y, they're aligned to the same axes, do they overlap, is what we're asking. All right, so if I was going to draw this out here, let's just get rid of that shape. And let's suppose I have 2 axes. I have the y-axis and I have the x-axis, right? And I have 2 shapes. I have the first shape that's over here and the second shape that's somewhere over here, right? Then we can say that, as an example, if I was to draw lines, right, from this shape, the verts of this shape to the x-axis, right, and the verts of this shape to the y-axis, right. If I was going to draw lines like this, okay, so I'm just extending. All I'm doing is creating a I'm basically just casting, if you will, a shadow, right, from this box, right, from each of the verts of this box onto the x and y axis. We're going to do the same thing when it's object aligned in a second. And so if you notice this box here, this is box A, let's say, we also, kind of cast a shadow, if you will, right? When we cast these shadows, you can see that, well, let's circle them now, and I'll put it in another color so you can see it a little bit more, a little easier. you can see that, well, there's no collision here or here because, you know, these ones are not really overlapping, right? So you got nothing overlapping here. But here, right, this one and this one, you can see that the shapes, this one and this one, there's an overlap, right? In order for my axis-aligned bounding box to overlap, all four of these things have to be overlapping. That means I've got to cast a shadow to the axes, that's how it really works, on for each of the boxes, right? If when I cast a shadow from each of these verts and they both overlap, then I have a different image here, right? Let's suppose I have a box now that looks like this. So let's do one of these. Here it's clear, and I'm glad that we did it in a different color. Here it's clear that if I cast the shadows again, so here I'm casting a shadow down to the x-axis, and I cast another shadow over to the y-axis, right over here, and then let's make the other one black, right? So then I do the same thing. You can clearly see that I'm overlapping twice, right? That there's an overlap here on both axes, and there's an overlap here. If there's an overlap on both axes, suffice to say that there's probably going to be a collision. Does that make sense? And that's what we're checking. We're checking to see that if, hey, guess what? Is this the distance between here and here? Is this the pixels that are here? Is this overlapping the pixels that are here? Yes. And how about the pixels that are here? Are they overlapping with the pixels that are here? Yes. If both those two checks are true, you've got a collision. And that's what we can clearly see here. Okay? That's how it really works. And if you think about that, that's what it says in our little pseudocode. So they're going to be axis aligned in world space. All right? And here's our little pseudocode. We're basically doing the exact same thing. We're saying that, okay, I want to get the first rectangle. We define two rects, all right, in this pseudocode here, where we have the x and y coordinates to the position of the first rect, right? And then you have your width and your height. And this position is the top left corner. 5, 5, with a width of 50 and a height of 50, all right? Rect 2 is 20, 10, with a width of 10 and a height of 10. So then what I do is I want to take the x coordinate of the initial rectangle, the start position of the initial rectangle. If it's less than the start position of the second rectangle, plus you add the width of the second rectangle, and these all have to be true, then you have a collision detection. It's exactly what we kind of say. We're going to basically, we're going to cast a shadow, right? Or as an example, or what we like to say in math is project, one axis or one edge to the axis. If we can project both edges to the axis, and if the lines overlap, both lines, then we're good to go. We know that there's a collision. Okay. And here they've just filling in the values. So if these are just variables and we fill in the values, you can clearly see that 5 is less than 30. That's check. We know that 55 is greater than 20. Check. 5 is less than 20. Check. And 55 is greater than 10. Check. We know that all of these match, and therefore a collision is detected. Now you might say there's a lot of comparisons here, and it's true. There's a lot of comparisons happening all at once, right? As an example. But again, when it comes to big O notation, because of circle-circle detection usually requires a distance check, usually AABB still is the simplest detection algorithm. Okay? Just from an efficiency perspective. When we think about 3D AABBs, we're going to get back to that. It's really the same kind of idea. We can extend the idea into 3 dimensions, right? Because now we have the third dimension and we're projecting onto the z-axis, the x-axis, and the y-axis from all of the verts as well. Okay, so it's kind of the same thing. We're going to get back to 3D collision detection in a couple weeks. There's also something called separating axis theorem. And this is a more accurate way of detecting collision detection, or to do collision detection. Why? We're basically saying this. If I can put an axis, right, between the objects, right, if I can form an axis somewhere between the objects, that's the theorem, there's no collision, right? If I can put an axis, some kind of thing between the two objects, there's no collision. right? So this comes from, or is derived from, OOBB collision detection, object-oriented bounding box. So let's go back to our drawing board here, for example. In object-oriented or OOBB collision detection, that's different than what we have here. Imagine if we're going to draw an object a little bit more freehand. Let's just draw it like this. So for example, I have an object where my box is not aligned according to the axes. What if I have this kind of situation, right? So I have this box, and you know what? I want to draw another box like this, right? Here's another box of a different size. They're not even boxes. They could be parallelograms. It doesn't matter, right? Two different objects. How then do we detect collision detection? We can't use AABB anymore, guys. We can't, right? It doesn't work. Instead, we need to do what we just did earlier, which is use verts. So again, we project our vertices only, not the edges now, down to the axes. So we can project this vert down to here. We project this vert down to here, this vert. And we do the same thing on this side. All right, that's what we're doing here. So we project the verts down to the axes, right? And then we do the same thing over here. So we say this vert has to be here. This vert is in there, right? This vert on this side. And notice there's also this one. We got to project them all. All the verts, as an example, have to be projected, okay? And the same thing goes here. So this one, this one, this one, and this one. Okay. So what we're saying here is the only way that we can determine collision is if we have enough vertices that are colliding. For example, this vert, right? Is it colliding? Is it overlapping with this one? No. But this one is, this one is, this one is. You know, as an example, there's more than 3 on this side, and there's more than 3 on this side. And this is how they figure out if there's a collision. Because on this side alone, we can clearly see that there's a collision detection. Here, there's only a couple places where we overlap. We overlap inside this area right here, right? So here's the overlap. Whereas on the y-axis, we overlap pretty much from, and this is the overlapping area right here, this part. Okay, this is the place where we overlap. And you can tell because there's many, many verts. These all this one, as an example, this one pretty much, and this one are all overlapping. You know, when it comes to the, you know, the spaces that are taken up by this one, and this one, right? Whereas it's not the same on the other side. So object-oriented bounding boxes work like that. We project onto the y and the x-axis, and we try and figure out if there's enough overlap. And if there are, we're good to go. And this is where separating axis theorem derives from. It comes from OOBB type collision detection. So what we're doing is exactly that. We start trying to project down onto the you know, the boundary. If we have one of these situations here, we have something like there's a separation. We can clearly see that there's no chance for collision here, right? Here, though, it looks like there's some kind of overlap on this side, but it has to be both. There can't be a gap only on one side. And here we can clearly see that this is not a bounding box. This is a triangle, a different kind of you know, object altogether. Okay, so both objects have to be touching in order for it to happen. So example, in axis or separating axis theorem, the first step to do is say take one side from one of the polygons, I'll be okay today, you are testing, and find the normal. All right, so that's kind of an interesting way of doing it too. I'm finding the normal from this side. Okay, so there's the normal. And then this will be the axis, as an example that we're comparing, because there is no axis. These are object aligned you know, elements as opposed to axis aligned, because this could be anywhere in space. And they could also be dynamically, you know, we're trying to dynamically detect collisions as opposed to static collision detection, which what happens most often. So now what we're saying is, okay, let's project down from the verts to this, you know, new phantom axis. So this is the same axis as from step 1. So again, this is step 1. We project down. We create a, you know, this normal. The normal becomes our axis where we project down. Okay, that's where it comes from. That's where this axis comes from, right? Then we project down from these points down to this axis. And then step 3 is we do the same thing. We just chose an axis, and basically we're projecting down onto this axis, right? So the second shape are projecting down onto this axis as well, all right? So now, do we have collision detection? Is there overlap between this one and this one, right? And the answer is no, because there's a gap, and they're not touching. There's no overlap, and there's no overlap. There's no collision detection. So the great thing about separating axis theorem is it's super accurate, all right? Because it doesn't matter whether you're using axis-aligned bounding boxes or object-aligned bounding boxes. Separating axis theorem, what it's going to do is it's going to find there's an axis that I can draw between the two shapes. I'm good to go. That's what I'm trying to do, right? On the downside, right, what happens is, so positive, it's pretty fast. Like, it's relatively similar to AABB style collision detection, because all we're doing is projecting down onto an axis, finding a normal, and we're good to go. It is super accurate. That's the good thing, especially for 3D. And this is where we use separating axis theorem the most, in 3D collision detection. All right. On the downside, it works only with convex polygons, right? When we have concave polygons, it doesn't really work that great, right? So that's a problem with that. And really, complex shapes are out unless you build them out of smaller convex shapes, which is actually another strategy for us when it comes to collision detection. One of the collision detection strategies we can use is we can combine colliders or collider shapes, right? So that we can create more of a mesh. But when we do such a thing, now we're doing multiple checks per object. Multiple checks per object equates to a higher number of computations per frame, which means it's less efficient. Okay? And this is where we're going with that. One other thing it does not tell you which sides are touching, only that how far they are overlapping and the shortest distance to separate them. That's all it does. So there's some disadvantage to using SAT. So here's the application. So we have a bunch of these verts. We have box 1 and box 2. And again, we can use these boxes to create, this is the pseudocode that we're going to use to start thinking about, right, preparing the vectors. We create all the vectors in place. And once we create the vectors, what we're going to start doing is we use this minimax projection on box 1, right, as an example, and then we do the same thing for box 2. And once we've done that, then we're going to say if it's separated, if the maximum projection from box 2 is less than the minimum projection from box 1, or the maximum projection from box 1 is less than the minimum projection from box 2. Looks like Node.js, yeah. Well, it is actually, I don't think it's JavaScript. I think the pseudocode is ActionScript, if I'm not wrong. Way back in the day. I know, Node.js. So that is really separating axis theorem. And that's pretty much what I wanted to talk about today from the 3 levels of detection. However, let's go back to our code for a second, all right? Because this is something that I want to address with you guys inside of the code. So I've provided a couple of things for you to help you with your assignment number 3. So one thing is, if I go back to my util.h, distances there that we've got. You can also calculate the normal between objects. Normalization is something that's not difficult to do. In my collision manager, what I've provided for you guys is a bunch of things. A line check, and I kind of showed you guys this, some of you, last semester when we did AI together. Okay, so we did AI together and we said, hey, look, you can do a line check where you kind of cross lines. If I can cross 2 lines, that's a very useful collision detection algorithm. The other one is a line rect check. So these are the things I've given you already, right? That do all the collision detections for you. And then a minimum squared distance between line and line. I've given you that. And a line AABB check, right? Which is different than a line rect check in some ways. Okay, so this is these ones are kind of combining to do this one. Also a circle AABB type squared distance check, or a circle AABB check. So different kinds of detection checks. All right, so squared distance, squared radius, AABB, and you can combine all these to create whatever you want. The other one is point rect check. This is a really important one too. So what are all these things that I'm talking about, and why am I bringing it up doing physics? Because you need it for your assignment, or you will. So let's talk about them in order. So let's talk about point rect check. What is that? Point rect check is I've got a rectangle and I want to see if a point is inside there. So I got, a point and a point out here, and I got a point in here, and I want to know if this point or this point is inside the rectangle. What do I do, right? So how do I figure this out? Well, it's kind of like it's an offshoot from AABB type thing. So if I go to definition, I kind of do the same thing. Look, this is the exact same algorithm as AABB for the most part. Top left, and then I look at the point. That's a point rect check. I have a point that I'm going to look at, and I'm going to have a rect start and a rect width and a rect height. Okay, which is exactly an AABB. That's what it is. Okay, and then all I'm doing is I'm saying, hey, if the point X and Y is inside, it's overlapping, then it's true. I have a collision. This is one of the most simplest and useful algorithms that we can use. Why? Because I can combine it with something else. If I want to know that a point anywhere on my line intersects with inside of an AABB, I can use a point rect check. Very, very useful and very accurate. If I did it too much, though, computationally, it's not a great algorithm to use for my entire... Imagine if I used every single point in a bitmap. That's pixel perfect collision detection, right? I'm checking every single point in a bitmap to see if it's inside of my rectangle. Pixel perfect collision detection. Super accurate, right? And sometimes we need to do it because there's no other better way of doing it, especially if you have some kind of weird, wacky object, right? So I can check. I can look at a bitmap, anything that's drawn inside the bitmap, any color that's in that bitmap, and I can basically check it to say, hey, is this point inside that place? Is this one inside there? Is this one inside there? And I can check with every single one. It can run through it fairly quickly, but imagine if I had many, many of those checks every frame. It's way too inefficient to do it this way. But this is great for single point detection. Okay. The other one is a line check. Okay, so line check is another basic one. So a line check basically says, okay, I've got two lines, right? I have a start and an end, right? Are these lines intersecting? No. Okay. Are these lines intersecting? Yes. Cool. How do I figure this out? And where is the point of intersection? I want to know where this is, this point right here, right? So a line check does that for us, and I've given you that. Guys, this is so important. Can you imagine if you want to do some kind of, and I showed you this before, some kind of AI line of sight? This is what this is. It's line of sight, right? Why? If this is the AI object, let's suppose I have an AI object way over here, right? And I want to see if I have line of sight to this point over here. And if I cast, we kind of did this before, if I cast a line from this one over here, do I intersect with any other shape before I get to this line here? If the answer is yes, if I intersected with this shape over here first, right, then I know there's no line of sight. It's pretty straightforward. And it can be done by doing a line check. Why? Because when I do a line rect check, I'm doing a line with 4 other lines. That's how it works, right? I do a line check with this one. Let's just redraw this just to get you to see it in a little bit more clarity. So here's my square or rectangle, whatever, and I've got a line, and I penetrate the rectangle this way, right? I'm doing a line check with this one. So this one, I'm checking this line here, right? With this line here. And I'm also doing a line check with this one and this line here. So all I'm doing is 2 line checks. Actually, what I really want to do for more accuracy, I do all the line checks, like all over. I check with this line, and this line. And if any one of these collide, then I have my line intersects the rectangle. That's how it works. Okay? And we can see that inside of the line check in here. So if I go back to my collision manager and I go to line check, go to definition, you can see exactly that. It's ugly, but that's exactly what it does. It takes my line start and my line end and my line to start and my line to an end, and I basically compare the lines. I have calculated the distance to the intersection point, right? And what this returns is, did it collide or not? And if I really want to, I can use something in here to find out where I'm colliding, not just if I'm colliding. Okay, so that's line check. So simple collision detection. So if I have line check, if I have point rec check, right? If I have line rec check, guys, I have a lot of different tools in my toolbox that I can use to detect different kinds of shape. Example, if I had some kind of weird shape. I'm going to draw another shape in a second. Let's just draw that together. All right, so let's draw another shape. I'm just going to use my fancy friend. So let's say I have a weird shape that looks kind of like this, right? And I want to do collision detection on this shape. And I want to have another shape that's over here. An example, here, let me just do another shape here. We'll make it so it's some kind of shape. Is there a collision? No, visually there's no collision, but I'm going to challenge you that if you tried to represent this shape, especially if this was some kind of weird bitmap, and if you tried to represent the shape on your engine somewhere, that, yeah, most likely it's going to register a bitmap or a collision. Why? If I was to surround this shape with a collision detection area, so let's say, for example, I did, logically, I did something that looks like this. Here's my collision boundaries, approximately, all right? So it's like the extremes, right, that I want to capture. Then you can clearly see that this shape here is inside the collision bounds. Clearly, right? Even if I used a circle or a cylinder or something else, I would still have a problem from a collision detection perspective, right? Circle might be the best in terms of, collision detection, right? Think about this. If I use a circle, I'm comparing centers. And depending on how my game runs, if my game runs up and down, I can do things like half heights. So if I did half heights, I can split this thing into half heights. So there's my half height here. And if I did half height here, so, this is half width. Let's do half height and half width. So let's do half height. So I'm running let's say my game is going this way, right? And if I was to do that, it's like I'm getting the radius, but I'm getting two radii, right? I'm getting the width and the height, and depending on where I'm coming from, let's say if they're traveling north-south, right? And if I compare the distance between heights in the centers, so I take this height here, and I take this height here, and I say, well, if I compare this height and the distance between the centers, this distance here, is this distance less than this one and this one combined? It looks like there is. So my circle check would fail because I'm inside the radius, right? If I come in here and I draw a circle, right, you can clearly see that I'm inside the radius of this thing. So the circle would fail too. So this is no good. Might be better, more accurate in some ways, but in this case, no. Right? So what do I do? How do I do that? Well, exactly what I did. I could represent this thing by splitting it up into smaller sectors, right? Like we did before, spatial partitioning, right? Where I kind of sit there and say, okay, well, you know what? If I broke this off and I said that especially for complex shapes, I said that, instead of making this whole thing a collider, for anything that's complex like this, I predetermined that there's a collision shape here. So let's just undo these things for a second. So I say, okay, well, I want to, create a collision detection so that it's more accurate. So I say, well, I want to make it so that there's more colliders, right? So I say, well, this is a difficult spot. So I think that there's a good chance that we put a collider, and we're just going to make it so that it's regular. Let's put a collider here. More colliders, all right? And we're going to do a collider like so, right? And we're going to see how this is also not going to be great. But it might be better, is what I'm saying, than what we had before. So then we had another collider there. And then we do kind of a collider that goes maybe something goes like this. And another one that goes kind of like this. If we're choosing it carefully, then we can get, and I'm just choosing them randomly. But if you choose them in carefully, you can see that, we might be able to make another collider shape that goes in a different way. So we sit there and say, well, maybe where there's a collider here, whatever. And we try and figure out the regions of this thing so that it only maps, what we're doing there. And it's like using calculus, like the area under the curve kind of thing is what we're doing, right? the challenge with this is, where do you separate? So again, from one angle, this shape is okay, right? And how far do you go? Do you go like narrow? Do you go really small? And I mean, if I make a lot of smaller, shapes, then obviously it's going to be more accurate, right? But now I have to check collision with all of these shapes as opposed to just one. The other thing to do is don't use collider shapes like this at all, but use lines instead. So, oops, let's just redo that one. Bring that back. Use lines instead. Well, we know that we can use line-line collision detection, so we draw lines, around the object, right? So we drew a line like this. More accurate. These are just lines. Now, you're going to say there's like lots of collisions. Yes, there are, but maybe not as much as boxes, right? And the great thing about this is you can capture a more accurate representation of what the collision shape is going to look like. Again, you can see especially in here that you're going to have a lot of collision, things, but it's going to be way more accurate still and not as expensive as pixel perfect collision detection, because that's really what I'm going to be doing. I'm just drawing shapes. I feel like a kid in art class, right? I'm trying to outline my shape with a bunch of lines, and of course I want to connect these lines as much as possible, right? You can create an algorithm to calculate the path, the shortest path, if you will, with straight lines around an object. And so now you're going to get a much more accurate representation, but many, many more checks. Now you can see that I'm going to do a line check 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, maybe 20 times, with 20 times 4. 80 checks I'm going to do every frame for these two objects, right? I'm just, ballparking it here. Is it more accurate? Absolutely. Is it reasonable? Maybe not. It really depends on how fast these objects are moving as well. The faster the objects move, we have to find out what is quote unquote good enough. Okay? Questions around the concepts that we presented today, right? Because these concepts are the things I want to talk about. Not that you don't know how to use an AABB type collider, all right? That's not the issue here. The issue is, what about complex shapes? How do you represent them? Because you're going to get to that point. What about if you have a player and he has or she has different appendages? An octopus, as an example. How do you represent that? Do you represent each of the appendages in a box, the whole thing? Or do you separate them all? What strategies are you going to use? What makes sense for you? And the answer is, always goes back to this, is it good enough? If it's good enough, if it looks good enough, and if it provides a good visual cue for the player to know that there's a collision, it's okay. Can we use splines? We can, but now we're talking about, again, a much higher, more difficulty. And you have to also understand how to use, math becomes, kind of goes off the charts when it comes to using splines. But absolutely, you can do it. There's absolutely ways of doing it as well. But if you're going to go splines, I might as well use spatial partitioning. Spatial partitioning might be the easiest way to do it, because I'm breaking up my entire grid, right, with how this is, right? So spatial partitioning, remember, I can make it so that I can use a grid, right? That's another option for me. If I know I'm going to have complex shape collision detection like this, then it's best, maybe in many ways, to create a grid for my entire game world, right? And then start splitting things off more and more. Apex, they updated a character's collision hitbox. I think this is a good way. Thank you for that. I'll take a look at that later. All right. Any questions around collision detection and complex and simple shapes? You guys should know how to do these things at this point. All right. That's all I wanted to talk about today. It's simple 2D collision detection. It should hold up any of the things that we've talked about when it comes to collision detection in the past. And I've given you some examples in our code that you could use for assignment 3. That's really what this is about. I'm going to stop recording at this point, and then I'm going to talk about the stuff about our Ubisoft faculty night. I want to talk about that a little bit before we end for the day.